Hello Year 13s and welcome to the very last video tutorial for Year 13 Algebra. And so in this video we're looking at using de Moivre's theorem for solving complex equations and how it sort of saves us a lot of fiddling about. So here, with our first example, we're solving the equation z to the 4 equals 4 plus 3i. So just remembering that z we often use for a complex expression, so we could expect a complex solution here. So if this was just z to the 4 equals any old number, you would simply take the 4 root of both sides. And that's the same as taking the quarter root of both sides as well. And in effect that's what we're going to do. We're going to take the quarter root of both sides so that we just get z by itself, and we're just evaluating 4 plus 3i to the power of a quarter. Now the only problem is that there's no easy way for us to evaluate a power when we have a sum of two unlike terms in a bracket. And so this is where the polar form of complex numbers becomes really useful. So we're going to put this into polar form and then we'll apply that power. So draw a diagram to help us visualize our number here. So we've got 4 in the real and 3 in the imaginary, and so our modulus is the first thing we'll work out, and that's going to be the square root of 4 squared plus 3 squared, which happens to be 5, which is very nice. So that side there is 5. Now we'll work out our imaginary component and our real component, so our adjacent and opposite sides. So sorry, what I mean is we will use those to find our angle here, and so we can say that tan theta, or sorry, we'll say theta equals, our argument equals tan inverse of 3 over 4. So let's bring up our calculator here, shift tan 3 over 4, put that in brackets so our calculator knows what it's doing, 3 over 4, and that gives us 36.87 degrees. So theta equals 36.87 degrees. Okay, so writing this equation in polar form, we're going to have z to the 4 equals 5 cis 36.87 degrees, and if we're wanting to solve this, then we're going to take the quarter power on both sides. So we'll take the quarter power on both sides, and so that leaves us with z, and we're going to take the quarter power of 5, and we're going to multiply our angle by 1/4 as well, so times 1 over 4. Okay, so the quarter power of 5, don't know that off the top of my head, so we'll find it. So quarter power of 5, gosh, that's smaller than I expected. I might apply that in as a fraction and see if that gives me a different answer. Nope. Okay, so that's we'll go 1.50 to 2 dp. So we'll say z equals 1.50 cis, and then the angle, we'll need to bring that up again. So here's my angle, divided by 4 equals 9.22 degrees. 9.22 degrees. Okay, now we'll just pause there for a second, have a little think about this, because if we have a power of 4, we've learned something earlier about what that means about the solution. So very quickly we'll get back to the fundamental theorem of algebra, which says any polynomial of degree n has exactly n roots over c, so that means complex roots. And so what we have to do here is think about what that power of 4 means. And what it means is that we've actually got 4 possible solutions. And so what we've just worked out here is only our first solution. And it turns out, so I'll just draw that on an Argand diagram so we can visualize it. So that's going to look something like this, where our argument is 1.5 and our modulus is 1.5 and our argument is 9.22. What it turns out is that the other three solutions happen evenly about the origin. And so all we need to do is add 90 degrees to our argument successively to get our 4 different solutions. And so our second solution is going to have the same modulus of 1.50, but it's going to be at 99.22 degrees. And our next solution is going to be the same modulus, but an argument of plus 90, so 189.22 degrees. And our last solution is going to be 1.50 cis, and it's going to have an angle of 279.22 degrees. And so that's the key that you have to remember when you're solving these equations using polar form, is that you're always going to have the same number of solutions as your highest power in your equation. Okay? Alright, so we'll move on to our next example, which is asking us to determine the cube roots of 8 and show these on an Argand diagram. So I might just, since it's one on an Argand diagram, we'll change to grids for a minute. Okay, so cube roots of 8. So basically it's saying z to the power of 3 equals 8. So it wants to find the cube root of 8, basically. So what we need to do first is write z3, that's in rectangular form, so you can, if you can imagine a plus 0 or a plus 0i, so we're going to write it in polar form. And so in polar form this is going to be 8 cis 0. And so if you can imagine that on a diagram, if that's our diagram, I'll get a different colour to draw the pen, to draw the number, then it's just going to be 8 on the real. Okay, so that's what 8 cis 0 means, and we have no angle there, so that's why we have cis 0. So I'll go back to our blue pen. So in order to solve this, we're going to have to take the third power of both sides, and so we're going to have to take the third power of 8, which is 2, and we're going to have to times the argument by a third as well. So 0 times anything is 0, so it's still 0. And so that's our first solution. So we'll write that on our Argand diagram. And so 1, 2, so that's 2i there, 1, 2, so 2, so that's real, that's imaginary, negative 2i and negative 2. Okay, and in a different colour we'll draw that result. And so 2 cis 0 is going to be here. Okay, now like I said before, because we've got a power of 3, we're going to have 3 solutions that are spread evenly about the origin, so about this dotted line. So we're going to have, whoops, we've gone off page here. So we're going to have one out here, and we're going to have one out here as well. Okay, now I've been working in degrees in most of the examples so far, so this time for a change I might work in radians. And so if you remember, for a circle the whole way around, that's 2 pi, and so if you're going, I did that in the wrong direction, it would actually be like that. Okay, and halfway around would just be pi, and so if these are evenly spaced, that angle there is going to have to be 2 pi the whole way around divided by 3, and then this space would be plus another 2 pi so and so on. So for our other two solutions, go back to blue. For our other two solutions, so that's Z1, for Z2, it's going to be 2 cis 2 pi over 3, and for our third solution, it's going to be 2 cis plus another 2 pi, so that'll be 4 pi over 3, and that's also the same as writing 2 cis negative 2 pi over 3. So those are the same result. And we've already drawn it on the Argand diagram there, or sketched it I should say, and that's about as good as we can get for a sketch without using a protractor and things. So that really highlights the fact that there are 3 roots of 8, whereas previously we've often said, well, 2 is the only root, but of course now we know the better that there are complex roots as well as real roots. Okay, there's one more example to go through today, and it's very similar. This is asking us to solve this equation, so we're going to take the quarter root of both sides, but only after we've defined this in polar form. So we're going to write z to the power of 4 equals 81 cis 0, and so we're going to take the fourth root of both sides, and I don't know off the top of my head what that is, so I'm going to go 81 to the power of a quarter, and that's 3. So our first solution, Z1, is going to be 3 cis 0, and our solutions are going to be spread evenly about the Argand diagram, so in intervals of 90 degrees, because we're dividing by 4, because we've got 4 solutions. So next one will be 3 cis, that should be 0, not theta, 3 cis pi over 2 if we're doing it in radians, and next one will be 3 cis pi, or 180 degrees, and our last one will be 3 cis 3 pi over 2, and that is our 4 solutions of that problem. So yeah, this really nicely reflects the fact that all these equations have the same number of roots as their powers, and once you get that process of putting it into polar form and then solving, making sure you distribute the solutions evenly about the Argand diagram, then this sort of stuff becomes your bread and butter, and it's very easy to get your head around. So we'll go on to exercise 13.04, and once you finish this, you'll be ready to concentrate on some targeted excellence and scholarship stuff.